So as Olivier mentioned, today we are here to present the way we built a new tabular benchmark, the philosophy behind it, why we did that, and where we are aiming at. By the way, I'm Alexandre Abraham, I'm lead AI scientist at New York, and I'm here together with Louis Ledin, who is my intern and joined very few weeks ago, and we'll work on that subject for the rest of the internship. You may have never heard of New York AI. We are a deep tech startup founded in Paris in 2024. We are currently working at Station F. And we are building NICL, a tabular foundation model specialized for industry tasks in particular. For now, we are targeting some verticals, peculiar verticals, in particular commerce, with partners like Auchan, Miracle, that you may have heard of. We are 13. We had 4 million in pre-seed investment from names that you probably know. What you want to know is why we are here today. As I mentioned, we are developing a tabular foundation model, and we wanted, obviously, to compare it to what's the existing models. And for that, we needed a thorough benchmark. So we looked at the one that were available, and we were not completely satisfied because we found that it was hard to make complex pipelines out of them. And the datasets are the one you usually find everywhere on all the tasks that we all work on with ML packages. And that didn't inform us a lot about how models could perform on industrial use cases. So we decided to target that problem. And what we would like to propose is a benchmark that is more oriented toward industry-grade tasks and their peculiarities. And we obviously want to give back to the community for all the great tools that the community is providing. So we want to share as much code as possible and share as many insights as possible. We will start with a small overview of the tabular benchmark landscape, and I will let Louis talk about that.
Thank you. So when talking about tabular benchmarks, the first question that we want to ask ourselves is why another benchmark? Because indeed, and specifically for tabular models, a lot of different benchmarks already exist. But a lot of benchmarks already exist, and they are backed by a very famous researcher, such as Frank Hutter, Artem Babenko, Gael Varocco, and leading private companies such as LG. But each benchmark brings different flavors to their studies. For example, TabArena focuses on handpicked, well-chosen datasets and proposes a living leaderboard. Lambda here focuses on integrating new models as fast as they're released. TabRed focuses on studying the strengths and weaknesses of Yandex models, tabular models. And CARTE is first the French benchmark, so Cocorico, and focuses on categorical features. Multitab, finally, focuses on explainability. When we ran the results of the second version of our benchmark, first thing that we wanted to do was to compare our results with those of pre-existing benchmarks. And then the nightmare began, because our results never agreed with other benchmarks. So this was something that kept us up at night. And then we took a deeper look at it and started comparing those benchmarks between each other on elementary datasets. And we came to the conclusion that even those benchmarks on pretty famous datasets, academic datasets, they do not always agree on the results, on the rankings. And for some datasets, pretty famous, for example, Credit G, we can find some models which are, for some benchmarks, the leading model, and in other benchmarks, the worst model. So at first, we were thinking, okay, maybe we did something wrong and we need to fix this. And then we came to the other question. There must be something else. There must be something about, it's not about the models, as shown here. It must be something else. It must be about the data. It must be about the pipeline, the pre-processing, post-processing. That's something we needed to focus on. And so that was a question we tried to answer.
Thank you, Louis. So yeah, the conclusion is that we needed to clear this up, and for that we decided to, alongside academic dataset that you usually find in benchmark, try to integrate industrial tasks. As I mentioned at the beginning, most benchmarks are made for very simple pipelines, and we need more complex ones. For example, if you're running deduplication on a product catalog, what you need to do is do some blocking, so iterating on subspaces, then generating pairs of features based on the pairs of products, and give that to your classifier. And after that, when you do the inference, the same process applies. You divide the subspace, which will have a different impact on your model, on your result. And all this complexity in pre- and post-processing make the results less interpretable, more fuzzy. So that's what we want to explore with our benchmark. For example, the typical, when you're doing generating features from pairs of vectors, you typically take similarity distances, norms. You can just put the raw vectors. All these features will have different distributions, but they will be the same across all the deduplication tasks. So maybe there is some insight to get from that. Some specific model can grasp these peculiarities in distribution. Also, we would like to know, with this complex pipeline and the model in the middle, what is the real impact of the nature of the model on the final result you get from your pipeline. Then we run into some problematic paradox. The problem we encountered is that when we take our pipelines and try to make them shareable, then the value of the pipeline disappears because we have operations that are tailored to the data that we cannot share. So paradoxically, we could share, let's say, degraded data with simple pipelines, and maybe you would see a difference in the model, but it's not interesting because it doesn't reflect what you get when you are in the industry context. So we had a lot of trouble with that. And in the end, what I said, what's most useful to share is what we can less likely to be shareable. So we decided to shift a bit our focus and first try to share our own pipeline package. You will say, oh, yet another Python pipelining process package. Yes, this is a package that allows you to make complex pipelines and run them in our benchmark. And still, we are trying to find the right level of transparency to share complex industrial pipelines. Another thing we envisioned, because we cannot share directly the data, is the path of the synthetic datasets, trying to generate synthetic data that looks like industry data, and at least on which the performance that you observe with your model reflects what you would get in the real industry pipeline. In the end, what do we bring to the table? We bring two things, our package, like I mentioned, and our benchmark. The package is what you can find in classical ML package pipelining tools. So you have different steps, you can run them, and you can model your simple or complex task. The peculiarity of this one is that, for example, deduplication is something you can pipeline with the blocking, feature pair generation. It's all available on the website. It's not the focus of the talk today, so I just evoke it quickly. The policy is to be very, very simple, very self-explanatory. So for each step, you will see the input, the output. It's all clear. It looks a bit like the ZenML interface, if you know it. And we bring the whole automation pipeline with debugging tools and clear outputs. For example, if you forget to give an input to a step, you will be gently reminded. And everything is packaged with extensive documentation. If you just run it in a Jupyter notebook, you will see that you can get a lot of information displayed in a nice way. I will now move on to TabBench, which is the focus of the talk today. I will go back to this benchmark comparison and position ourselves. So TabBench is the benchmark that we developed. The first version that was previously released has 50 datasets. And the second version, for which I will give some sneak peek today, goes up to 200 in order to cover all the classification datasets that are present in TabArena and Lambda, for example. The goal of this step is obviously to see a more fair comparison across the different benchmarks. And our focus is on industrial task and explainability, so we'll detail after. So we also provide industry-grade datasets. Those are private datasets. We only provide the results. What we propose is that if you have a model that you want to test on this private dataset, you can reach out to us, and we will run it on our data. And also, if you feel like integrating your dataset, we can integrate it in our private vault. So do not hesitate to reach out. We had 36 tasks in the first version, and we are moving to 65 in the new one. We compare we compare foundation models, because that's the focus of our company, but also decision trees and MLPs. And the new release brings modern models like RealMLP, TabM, Modern NCA, and also ensembling, because that's a remark we had in our first benchmark. This part was missing, so this will be added. For now, you can look at the results of the first version. We have a dashboard that you can reach at dashboard.newarkai.com. As you can see, it's a presentation of all the results. You can get them with different metrics. You can look at the aggregated results. You can look at the results per datasets. You have really all the information we have from the benchmark. We also have an industrial dataset tab where you only get a summary of the results. And you can look at the whole pipeline, see how each model performs on the individual datasets. What are the results in the end, the interesting part? So if we compare the model by rank, the lower being the better, we see that the foundation models usually are in the first position. They have really a strong block. And then comes the gradient-boosted decision trees. And finally, the MLP, the way we coded it, was the worst one in our first benchmark. And a sneak peek to the new results bring a different view, because the foundation model are still leading. But we see that the modern models like TabM, Modern NCA, are really taking over those ones. They are chasing them. One thing, for example, that we would like to dig more into is the fact that our results on Modern NCA are better than the other benchmark. So that's something we are still investigating. What we did, well, we didn't make that on purpose. So what did happen? This is something we would like to explain better. We did the same, obviously, for industry-grade datasets. Once again, the foundation model are leading, and we observe the same pattern. So that tells us that, in the end, the overall performance on industrial dataset is something that matches the academic ones. Yet, from our experience, the insight we get from the end-to-end pipeline is different. And that's why we would like to convey to the community once we have found a way to properly share the pipelines. And the same sneak peek to at the new results on 65 datasets. We have still the same insights. Foundation models are leading. and, but we find a larger gap with the other methods. So we will continue to investigate this. What we would like to have here is inside people who have industrial use cases that they could share to come to us, because for now we have, as you can guess, we have some difficulties to convince people that so these results should be shared. So we are welcoming any contribution. On industry-grade dataset, so we propose a fair comparison on the model, and you can have a real-world usefulness idea of the different models. And still, we want to share as much as possible without sharing the data. So the next thing we did was trying to generate synthetic datasets that resemble the industry-grade dataset that we propose in our benchmark. I will move on to this part. What is the purpose of synthetic data? The ideal setting that we would like to have is actually have a kind of projection of the dataset on a 2D plot with industry on one side, academia on the other side, and we want to bridge the gap between the two using synthetic data. This is a bit the gist that we had. And the goal of this synthetic data will be to share them and to bring more insight about the predictions of each model. The hard part was to find a clever way to project the dataset in a 2D space. What should we use? For example, multi-tab does the analysis with a number of categorical features, a number of rows, ratio of missing data. So indicators on the dataset that are very common and don't bring a lot of information about the complexity of the task. So we take another point of view and try to model the complexity of each task. For that, we take random columns as targets in our datasets, and we try to predict them from the other ones using a simple model like a random classifier, random forest, logistic regression. And we look at the quantiles of distribution of performances. That should give us an idea of how complex a dataset is and how each model that is based on different hypotheses sees the data. That's a bit the intuition. So that's what we did on academic datasets, synthetic ones, and industry ones. The result is this TSNE projection. What's interesting to see here is first, so you can see in pink the OpenML datasets, in blue the industrial ones, and in green the synthetic ones. The first thing that you can observe is that we really crawl a lot of space and even beyond what the academic industrial datasets cover. So we really span as much as we can. We may reduce the focus a bit later to more realistic settings, but that's good news that we are able to crawl all the data manifold. You can see at the bottom, most of the pink, so academic datasets are in the cluster at the bottom. So they share more or less the same complexity. We have a bit more at the top, but it's a minority. And here I highlighted in red 2 clusters of industrial datasets. Some of them are also shared. I don't know if you can really see it clearly here, but some of them are also present inside the blob of data. What's interesting here is that we see that the industrial datasets have a peculiar complexity, and actually some academic datasets seem to be sharing that complexity. So one step could be to first investigate deeper what these academic datasets are telling us and why are they so close to the industrial ones. And obviously what we would like to do is therefore to try to use the synthetic dataset to have a better view of the performances of the models. In conclusion, what we found is that the academic tabular benchmark landscape is a bit fragmented and opaque. The results are not always consistent. And when you're a practitioner, it's hard to determine what model you should use in which case. And the thing we observed, and the reason why we didn't share more pipeline, is that the raw task performance of the classifier inside the complex pipeline doesn't clearly reflect its performance in the whole process. So we are still trying to figure out this problem. Yet we want to have some help, so that's why we shared our toolbox that can allow you to run complex pipelines, and we are eager to collaborate if you want to try. And also we have generated those synthetic data that for now it's very early results, so we still need to investigate further, but the results are very promising, and we hope that it will bring a new light on the benchmark. In the next step, we would like to share more about industrial tasks. In particular, we will be trying to understand why some benchmarks are having different performances. In particular, is it related to some or peculiar pre or post-processing? And we would like also to integrate new tasks. For now, we have the industrial dataset I presented are categorization tasks, so it's a multi-level classification of products. We would like to integrate more like deduplication and recommendation. We are looking very eagerly for new datasets and use cases, so do not hesitate to reach out if you want to collaborate. Thank you.
So we have time for a few questions.
Hello. I have a question about the benchmark comparing the various models. So you said the foundation models were doing better than all the others. And I wanted to ask a very naive question. So how did you retrain these foundation models? And how did you fine-tune, or how is it done?
So for now, the TabICL and TabPFN are the ones you can find readily on their repository. There is no fine-tuning. We just use the plain and simple version. For the datasets that are exceeding the limits of TabPFN, for example, they provide strategies, because TabPFN is supposed to be limited to 10,000 lines and 10 classes. So they provide strategies to go beyond that. But we know that it dampens a bit performance. So we use these strategies because we have no choice. In Tab Arena, for example, they replace TabPFN and TabICL when they cannot predict by the performance of gradient boosting strategies. And for Nickel, this is our own model, and we do not disclose details about it yet. But you can maybe look a bit at what we already shared about it. But yeah, I cannot detail more this model, sorry.
Hi, thanks for the talk. I have another question about these model ranks. I was just curious to know how the data processing pipeline impacts the model ranking. I mean, how the results are robust to different architectural decisions. Is it clear?
Yes, it's perfectly clear. That's a bit where we want to go with the next step of our pipeline, is to find the real impact of the pre-processing. For now, what we've done is taking the pre-processing that performed the best for each model. For example, if I take a simple example, all the gradient boosting strategies now will handle the categories automatically, so you don't need to one-hot encode or anything. We tried the different strategies and we take the best result. That's what we do for now. We also do some hyperparameter search for each of them. And we didn't really look at the raw results and the results with hyperparameter search. We just put the best one for now. But we had this remark because in TabArena, for example, they provide results for the default model, the tuned one, and the ensembled. And we will provide the results for the, with the ensembling strategy. And also, that's our goal to go beyond that and provide more detailed results for the preprocessing. That will be our next step, actually.
Thank you.
Thank you for your talk. I have two questions. So I was looking at whether those benchmarks were accessible on your website. Is it the case or not?
Sorry, I didn't hear the question.
Are those benchmarks accessible on the website or not? Those ones, just what you're showing actually.
Yeah. They are all available. You can rerun them if you want, yes.
Okay. And so when you specify the average rank here, can you give some more detail about what it is?
Yes, so those plots are made using a package called AutoRank. It's a package made to compare the ranking of the data sets. What it does is a Friedman test with a post-hoc Nemeni test. You can find the statistical details on their website. We usually share the rank, despite the fact that we know sometimes the rank is not really informative because the difference in the metric can be small. That's why this is a result that seems maybe the most understandable for the talk, but if you want the accuracy and everything, they are also available. I will just pause on the right moment. You can have all the accuracies here. You can look at F1 score, everything. So if you want more metrics, they are available on the website.
I have a question when I'm walking. You mentioned that for the industrial datasets, it's quite challenging to find the right complexity level and to reproduce it using synthetic data. Have you tried to write the causal mechanism of the word for a specific task, for instance, catalog deduplication, and simulate it with a causal structure so that it better captures the word complexity and have a better chance of replicating the distribution?
Yes, we didn't try that, but it's definitely on our roadmap. we just didn't have time. When I said that sometimes the pipeline can be determinate, is, for example, if you look at the specific task of deduplication, you will find a lot of packages that exist, and most of the time they will try to find a column in your data or a set of columns for which the unique match or fuzzy match will inform about the duplication. And this is something that works very well and that will clear out some of the samples that you want to deduplicate, for example. And we cannot share it, so that's why it's hard. Sometimes you have very simple strategies that can totally change the shape of the problem. So we are looking in ways to convey better information.
Thank you. Very nice talk, very interesting. I have a question about the comparison with classical machine learning algorithms, because they tend to perform better if you do right hyperparameter search. Also, we need the feature engineering, contrary to the foundational models, which has representational power by themselves. How did you handle that?
So like I said before, for now, what we did is when we had insight about how preprocessing could impact the result, we tried different preprocessing and took the best one. But nowadays, most of the models come with their own preprocessing. If you look at TabPFN, TabICL, you don't need to preprocess them. They will take your raw data and apply the preprocessing that is the best adapted to the model. But if I take an example of something we want to dig deeper, is, for example, TabM model, the Yandex model, TabM, TabR, and MLP-PLR. They are pretty simple in their architecture, and they work very well because they have a peculiar preprocessing, which is the LTDL embeddings for those who know the name. And this is something, for example, that as far as I know, have not been tried in combination with trees or with other models. So for now, we use what's shipped with the packages, or we do some quick cross-validation, we take the best one. But in the future, we want to go further investigating that part, yes.
Okay, thank you very much for the presenter and the questions. So please thank them again.